Welcome to section 3.6, which is graphing our functions. So basically we're going to take all the fun we had in section 3.3 and 3.4, talking about increasing, decreasing, relative extrema, concave up, concave down, points of inflection. We're going to take all of that with our sentences, find the y coordinates that belong to all our special points, and graph it. So we're going to kind of refresh our memory on a lot of things that we have used in the past to graph functions. The first thing we look at is our polynomials. We always usually look at the x and y intercepts. We look at the highest powered term to determine right, left-hand behavior. We connect the intercepts with a nice smooth curve. Well, the problem is, usually if it's in function notation, we have no problem finding the y-intercept. The x-intercepts can be very difficult to find if they don't factor, if you can't use your calculator. Oh my gosh, there was that Descartes rule of sign. Yeesh, we don't remember. So we have other techniques we will need to use. And hello, calculus. Calculus is going to help us get that done because a lot of these things are going to be without the use of a calculator. So we can't just plug it in and poof, there's our answer. So just to refresh our memory, the first derivative is going to help us figure out if we're increasing or decreasing. When the first derivative is positive, we're increasing. When the first derivative is negative, we're decreasing. We can use that to find our relative extrema by putting those critical points on a little number line. Okay, if we are negative then positive, that means we are decreasing then increasing, so we're a relative minimum. If it goes the other way, however, critical points, we're positive then negative, that means we're increasing then decreasing, we're relative max. Concavity, if our second derivative is positive, we're concave up. Remember, that looks like this guy. Second derivative less than 0, we're concave down. Where our second derivative is equal to 0 or undefined, that is a possible point of inflection. It has to change signs. It has to be positive on one side, negative on the other side, because there has to be a change in concavity for you to be a point of inflection. Now remember, the second derivative can be used to find that relative extrema too. Plug that second derivative into your original function. If it's positive, you're a min, negative, you're a max. To refresh our memory on rational functions, usually finding the x and y intercepts not a big problem. X-intercept, set the numerator equal to 0 and solve. Y-intercept, put zeros in for all the x's, solve. Vertical asymptotes, you're going to look at the denominator and set that equal to 0 and solve. Remember, they are going to be in the form of x equals. Horizontal asymptotes, you're looking at the highest powered term on top against the highest powered term on the bottom. If the numerator's power is smaller than the denominator, then you have a horizontal asymptote at y equals 0. If the powers are equal, you look at the highest powered term on top, the highest powered term on the bottom, look at those coefficients. Y equals a over b is going to be your horizontal asymptote. If the power on top is bigger, you don't have a horizontal asymptote, you will have a slant asymptote or an oblique asymptote. To find your slant asymptote, you are going to divide and throw away your remainder. So it's still going to be in the form of y equals that quotient without the remainder. So any remainder, you're just going to cross it out, you're not going to count it. Symmetry, just a little check on symmetry. If you can put in a negative x in for all the x's in your equation and simplify, and it's exactly the same equation as you started with, that means you're symmetric with respect to the y-axis. If you can change all the y's to opposite y's, then you're symmetric with respect to the x. If you can change both, you're with respect to the origin. So if you're looking at an equation that has all even powered x's, you got a good shot at being y-axis symmetry. If all the x's are even, then you have a shot at y-axis. If all the y's are even, x-axis. If all of them are even, all of them are odd, you've got a good shot at origin. Remember, there's another way to discuss y-axis symmetry. Even is another way to talk about y-axis symmetry. Odd is another way of saying origin symmetry. Remember, all extrema, all points of inflection have to be in point form. Woo! Lots of stuff we got to cover. Here we go. Now when we graph it, we're still going to have to state our increasing, decreasing, concave up, concave down, relative extrema, points of inflection, everything we did in section 3.1 to 3.4, except now we get to graph it. Hallelujah. Here we go. So find that first derivative. That's going to be 3x squared minus 3. Now remember, we got a lot of things to find, so we might as well go ahead and get started. We are going to set this equal to 0, and we are going to solve. So if we set that equal to 0, and we need to show that we're setting that equal to 0. So once we do that, you can factor it or go ahead and solve for your x squared. Either way, you should get the right answer. Be careful about factoring things away. This does factor. Okay, so don't divide by variables. Don't divide by any numbers because we need to know if it's positive or negative. So I have critical points at x equals positive and negative 1. So if I look at my little chart here, and remember this chart is just for us, negative 1, positive 1, I can see that if I pick 0, 0 is going to be a negative for my first derivative, so it will alternate because of my factors. Okay, so I know I'm increasing on the outsides, decreasing on the inside, and I just always draw a little picture for myself. I'm increasing, then I'm decreasing, so I know negative 1 is a max. I'm decreasing, then increasing, so I know 1 is a minimum. This chart does not get any points for justification. We have to write the sentences. So let's get started. Okay, my derivative is greater than 0 from negative infinity to negative 1 and from 1 to positive infinity. So y is increasing on that same interval from negative infinity to negative 1 and 1 to positive infinity. Okay, my derivative is less than 0 from negative 1 to positive 1, so y is decreasing from negative 1 to positive 1. Okay, now we can say y changes from increasing to decreasing, or we can say our derivative changes from positive to negative to describe our relative extrema. It's all in your personal choice. Since y changes from increasing to decreasing at x equals negative 1. X equals negative 1 is a relative max. Okay, since y changes from decreasing to increasing at x equals 1, x equals 1 is a relative min. Okay. Now let's find all of our information with our second derivative. Let's pop that in right here. So if I take the derivative of 3x squared minus 3, that's going to give me 6x. If I set that equal to 0, I've got a possible point of inflection at 0. Okay, so if I do my little chart, remember this is only to keep ourselves organized. If I put in a value that's negative, my derivative is going to be negative. If I put in a value that's positive, my second derivative is going to be positive. Let me see if I can squeeze it all in here. Oh my goodness, there's a lot of sentences to write. So our second derivative is less than 0 from negative infinity to 0. So y is concave down from negative infinity to 0. Our second derivative is greater than 0 from 0 to positive infinity. So y is concave up, oops, concave up. From 0 to positive infinity. Okay, y changes concavity. At x equals 0. So x equals 0 is a, oops, I'm running out of room, a POI. I apologize for it being so messy. Try to do better on the next one. So we've got all of these relative extrema, all of these critical points, etc. Well, I need to know what those points are. So I need to come back up here to the original statement and find out what the y coordinate is. So I've got a relative max at -1, I've got a relative min at x equals +1, and a point of inflection at 0. I need to know what those y coordinates are. So I need to plug them into the original equation to see. Well, if I plug -1 in here for all my x's, that's going to give me a y value of 4. If I plug 1 in, that's going to give me 0. If I plug 0 in, that's going to give me 2. Once again, the only time you go back to the original is to find the y coordinate. So now I can plug those points in and make a nice decent graph. 1, 0, and then -1, 4. So when I draw this, I'm going to be increasing, decreasing, and then increasing. Whoops. Let me try it again. Hand-eye coordination. We're concave down, we're concave up. I had to redraw that because I accidentally swooped down past my relative min, and I don't want to do that. I want people to see that my max is here at -1, 4, and my min is at 1, 0. Okay? Now, I know these problems, there are a lot of things to do. These problems are worth a lot of points on your test, so don't think there's going to be 100 of these on your test. There's only going to be 1 or 2 or 3. But on free response problems, on multiple choice problems, they may have just one of these little statements talking about if the derivative is greater than 0, the original function is. We want to make sure that we've practiced enough to know that if my derivative is positive, I know I'm increasing. Okay. Now with this one, we've got a little bit more fun because we have rational function. We have the ability to talk about x-intercepts, y-intercepts. If I find my x-intercept, that's going to happen at -1. I know I have a y-intercept at 0, -1/4. So there's a lot of things I already know about this function without using calculus, and if it's a multiple choice problem, I'm allowed to use all of that information. I know I've got a vertical asymptote at x equals 4. I know I have a horizontal asymptote at y equals 1. Now the thing about it though is if it's a free response problem, we have to use calculus to solve it and to justify it. Multiple choice, I can figure out my answer using all of the knowledge in my head. Alrighty, so if I look at my first derivative, now remember I'm going to be using the quotient rule, so the derivative of the top is 1 times the bottom as is, minus the derivative of the bottom, which is 1 times x plus 1, all divided by the denominator squared. So my first derivative turns out to be -5 over x minus 4. Okay. So I do have a critical point. My critical point is coming from where the denominator is equal to 0. So somehow I need to show that. So I'll put my first derivative is undefined where my denominator equals 0. So that's going to give me my critical point at x equals 4. There's no place where the derivative equals 0, so this is my only critical point. Now this critical point, because it comes from the denominator, it's not actually in the domain of my function. It's where my vertical asymptote is. So he will never grow up to be a relative extrema, but he will be able to split things into, oopsie, that's a square by the way. It could change from increasing to decreasing. Now this little guy, there's all kinds of trouble because you've got that quantity squared at the bottom. So I'm negative on this side, negative on that side. So 4 is a critical point, but it just doesn't change any increasing, decreasing. It's not a relative extrema. So there's something going on at 4, but the first derivative really doesn't show me much. When I write my little sentences out, I'm going to leave a little bit of space. Okay, so my derivative is less than 0 from negative infinity to 4 and 4 to positive infinity. My function doesn't exist at 4, so I can't write it all in one nice little interval. So I'm less than 0 from negative infinity to 4 and from 4 to positive infinity. So f is strictly decreasing and therefore has no relative extrema. Okay, so we got it all out in one nice happy little sentence. Okay, so now let's talk about our second derivative. Okay, I'm going to put our second derivative right here. I apologize, this is so messy, but there's really no way to get it all on one screenshot without it being messy. Now when I do this, my second derivative, I am going to pull this up, so I'm actually looking at negative 5 times x minus 4 to the negative 2 power. So when I take the derivative, it's going to be 10 times x minus 4 to the negative 3rd power, which is 10 over x minus 4 to the 3rd power. Once again, my only possible point of inflection comes from 4. I know it can never be a point of inflection because 4 isn't a point on the graph. So I'm not going to have a POI. I'm not going to have a relative extrema. Thank goodness we know a lot about this graph because there aren't a lot of points to pick. On the left side of 4, my second derivative is negative. On the right side, it is positive. So we do have a change in concavity. It's just where it changes concavity. It's not a point. It's not a real boy, Pinocchio. So we are greater than 0 from 4 to positive infinity. So f is concave up from 4 to positive infinity. My second derivative is less than 0 from negative infinity to 4. So f is concave down from negative infinity to 4. Since x equals 4 is not in our domain, there are no points of inflection. Okay. So when I go to graph this, I'm going to graph all the information I already know. I've got a vertical asymptote here at x equals 4. I've got a horizontal. Oh my goodness, what happened? There we go. And then at y equals 4. Gracious. Can't find the line there. There we go. I know my x intercept is at negative 1, 0. I know my y-intercept is at negative 1/4. Okay. Now, looking at my function, I know my function is decreasing all the way through. So I know my graph on the left side of that is going to come down in nature. So that tells me about what's happening on the other side of my vertical asymptote. My graph is decreasing, so it couldn't be down below the axis coming up because that would be increasing. So I know already that my graph has to be up here because that's the only way it can be decreasing on the left side of 4 and decreasing on the right side of 4. So even not knowing a lot of points, I can tell you what the behavior, what the shape is of that graph. All right, so you have an example to try. And then, I think you have 2 examples to try. So you've got 2 examples. See what you can do. Oh, we're going to do number 5 in class together because there's domain problems and all kinds of good stuff. And look at this. We've got the original function. We're going to graph the first derivative. We're going to do that in class as well. So make sure you show up. It's going to be a fabulous day.